This lecture focuses on an application of integration to an interesting problem in fluid dynamics, which is the determination or measurement of hydrostatic force and pressure. To begin the discussion of this topic, let's consider a simple scenario where we are measuring the force exerted by some weight, a cube of material, on a horizontal surface, which is shaded in this figure. If the mass of this block is, let's say, 5 kilograms, we can calculate the weight as we have before using the expression or the formula weight equals mass times acceleration using acceleration due to gravity. So we get 5 kilograms times 9.8 meters per second squared, which gives us 49 kilogram meters per second squared, or in more familiar units, 49 newtons. So that's the force being exerted downward by this mass. We're also interested in how that force is distributed over this region upon which the mass is situated, this square horizontal region. If this region, say, has area 4 square meters, maybe the square is 2 meters on a side, then a useful quantity to calculate is the force per unit area. This is the pressure exerted by the mass on the plate. So we can calculate this pressure by taking the total force, which is 49 newtons, and dividing it by the area over which that force is distributed, or 4 meters squared. That's 49 newtons over 4 meters squared. This gives us 12.25, and the units here would be newtons per meter squared. This unit, a newton per meter squared, is used so frequently in applications that it's given another name. 1 newton per meter squared is called a pascal, so we could just say that the pressure exerted by this mass on this region is 12.25 pascals, or PA for short. Now that's the calculation of pressure exerted by a sort of a fixed mass, a block of wood or metal or whatever you have. We're interested in this section, as we mentioned, about fluid dynamics, or forces exerted by fluids. In particular, the force exerted by a body of water if you find yourself at a certain depth below water. So in order to discuss that kind of scenario, let's consider, instead of a mass on a plate, let's consider a horizontal plate submerged under a large body of water. So here's our body of water, and let's pretend or suppose that the water level was pictured as follows. And let's suppose, for the sake of concreteness, that our plate, which I'm shading down here, is at a depth of 10 meters. And let us further suppose that, as before, our plate is 2 meters on a side. Okay, so now we'd like to calculate the fluid force, or the pressure that is experienced by that plate on this column of water. So the interesting fact about fluid dynamics is the following: that the pressure exerted, or the pressure, I should say, experienced by this plate, the only contribution to that pressure is the column of water which lies directly above the plate. So all of this stuff out here, all of this water, this plate could be submerged 10 meters deep in the middle of the Atlantic Ocean. All of the water that's outside of this region directly above the plate has no bearing on the pressure experienced by this plate. The only water that we have to take into consideration when calculating the pressure is the water directly above this stuff in here. So to calculate the pressure experienced by this plate, well, we need to do a calculation very similar to the one done above. First, we need to calculate the mass of the column of water which is directly above a plate. So what's that mass? Well, the mass of the column of water can be calculated by taking the volume of that column times the density of water, which is a known physical quantity. What's the volume here? Well, the volume is just the volume of this box. That's 2 meters, 2 meters times 2 meters times 10 meters, or 2 times 2 times 10. What's that? Meters cubed, right? The density of water is a well-known 1,000 kilograms per cubic meter. So we can calculate this. What do we get here? We get 40 times 1,000, or a whopping 40,000 kilograms. That's it, of mass, right? So that's the mass of the column of water suspended above the plate. To calculate the pressure, we now take the total. Well, I'm sorry, I skipped a step. Before calculating pressure, we need the force, or the weight, of the column. Of course, force exerted downward by the column is identical to the weight of the column of water, and that then is obtained by multiplying the mass times acceleration due to gravity. And for that we get a large number, 392,000 newtons of force bearing down on that plate. So that's the total force, but then if we want the force per unit area, that's the pressure. So we can calculate, again, that pressure by taking the force divided by the area of the plate. So we get this 392,000 divided by 4 meters squared. I'm suppressing units right here. I'll add them at the very end to obtain. We obtain 98,000. So what are our units here? It's newtons per meter squared. That's the unit of pressure. And again, of course, a newton per meter squared is a pascal, so we can just call that 98,000 pascals, or PA. Now, typically in business industry applications, these pascals come in pretty big measurements, like 98,000. So it's more common to work with the unit of a kilopascal, which is 1,000 pascals. So this would often in practice be abbreviated by 98 kilopascal, which is abbreviated kPa. So that's the most sort of reasonable answer for this question. Now here's the scenario that we're interested in for this discussion. We're interested in the fluid pressure exerted not necessarily on a horizontally situated plate, like this one I just drew, but instead we're interested in the fluid pressure exerted on a vertical plate. For example, one scenario where this might be a really useful and important number is a scenario where one has constructed a large hydroelectric dam. So we have a large body of water right here and a very large concrete wall against which all of this water collects. And then, of course, in a hydroelectric dam, you have all sorts of mechanisms for funneling the water through the dam to drive turbines and thereby create electricity. That's another fascinating story, but that's beyond the scope of this conversation. It's important, at any rate, to measure the total pressure exerted by this large body of water on this vertical concrete wall. Now, there are two issues which make this a more complicated calculation than the one we did above. The first complicated issue is that the face of this surface may not be a perfect square like we had above. If we're looking face on at our hydroelectric dam, it might have a shape looking something more like this, perhaps a trapezoid. So we have land here, and then this trapezoid would be submerged under the body of water, right? That might be a reasonable shape for a dam, or at least a trapezoid would be a good approximation thereof. So that's one issue. So we have to worry about calculating the area of this trapezoid. The other problem we're going to encounter is the more significant one. That is that the pressure exerted on the dam, say at this point right here, will be drastically different from the pressure exerted on the dam, say at this point right here, precisely because this point is at a much greater depth than this point right here. And that's where the notion of an integration or an integral will be key in this process, because we'll have to add up the contributions of forces on infinitely many layers of the dam as we descend down the depth of the surface. So that's sort of the setup for this section, and that's what we'll do in detail in the next video. I will mention one more sort of subtle point before we stop this video and move on to the next one that I glossed over just a moment ago, and that is, previously we discussed the pressure bearing downward on a horizontal plate, but now I'm talking about the pressure sort of exerted sideways, if you will, on a vertical plate. And it may be confusing to equate or to move back and forth between those two different pressures, but the experimentally verified and accurate fact here is the following interesting point. If you pick any point here below the surface of the water, then the fluid pressure exerted by the water is the same in all directions. So that is a postulate or an axiom that is experimentally verified and that we will accept and use for this lecture. So if I pick a point, say right here on the wall of the dam, the pressure exerted in a sideways manner, which is the pressure we're interested in, is the same pressure as the pressure exerted downward at that point. So we don't need to worry about the horizontal or vertical, orientation of the point, because pressure is exerted equally in all directions. And that turns out to be a really convenient and labor-saving assumption and fact about fluid dynamics. So in the next video, I hope you'll hop right along to it. We're going to discuss this problem, the more general and interesting problem of calculation of fluid force on a vertical wall whose points are at varying depths below the surface of the water.